All right, so this video is to replace the first 15 minutes of my messed up enzyme video. So if you're following along in your notes, we're on the front page where it says AP Biology, Energy, and Enzymes. We kind of got through this stuff, and so the part that was not good in the video, the content part that was not good, was thermodynamics and then exothermic versus endothermic reactions. So, other than that part, I'm going to be on the whiteboard the whole time. So let me go ahead and switch cameras on you. Okay, so for thermodynamics, the first law of thermodynamics is something that you've heard before. That's the conservation of energy law. That says you can't create or destroy energy, but it can change forms. So if I've got these lights. They convert electricity, that's one form of energy, into another form, light energy. And so the first law of thermodynamics says you can't create or destroy energy, but it can convert from like wind in a wind turbine to electricity, or a light bulb from electricity into light, for example, or gasoline could be chemical energy, and then we convert that into kinetic to make the wheels go. So we can't create or destroy energy. It can only change forms. And then generally, the second law of thermodynamics, though, says that anytime you look at energy, well, let me back that up. So the first law of thermodynamics is you can't create or destroy energy. It can only change forms, but one thing to kind of keep in mind is whenever it changes forms, you usually give off some of it as heat. So that's why, like my phone, if my phone was working really hard, uploading or downloading something, it would feel warm. It's not because the manufacturer wants it to like heat up. It's that they're wanting it to just function, but as a default, it gives off a little bit of waste heat. And that kind of relates to the second law of thermodynamics. The second law of thermodynamics is the entropy law, E-N-T-R-O-P-Y. And that's the law that says all things fall apart, or all things tends towards chaos, or all things go from order to disorder. The entropy law is the reason why I have to eat food. Right now, I'm a bunch of organized cells, but if I don't eat, I'll die, and then eventually I become completely disordered. I become soil, right? So I don't want to die, so basically, the entropy law says all things tend towards disorder, unless you input energy. So as long as I eat food, then now I can maintain this order. But if I quit eating food, I end up as dirt. As far as what does that have to do with biology, it kind of has to do with biology because that explains like why I eat. Thermodynamics doesn't come up a whole lot in AP Bio, but if you're in an energy unit, then you have to still kind of understand those things. So it requires energy to maintain organization is the main application of bio. The next part, exothermic and endothermic reactions. So you studied these in chemistry for sure, and you might revisit them in physics. I'm not real sure. Sometimes AP curriculum in the past used to have Thermo in it, AP physics, and then it didn't or something like that. So I don't know where they're currently at with that. But reactions. So if I look at these two graphs, this over here says energy, calories. That's time in milliseconds. Again, energy and calories, time in milliseconds. On your notes, it says something slightly different. It says like progress of the reaction. But basically, it starts at the beginning and continues on. So the progress of reaction is still like from the beginning to the end. So it ends up being a similar thing. Over here, it says potential energy of the molecules, energy. In your chemistry class, you probably didn't use calories. You probably used joules or something like that. But in bio, we generally use calories. So if I have a reaction that looks like this, that means my reactants started over here, and as time went on, my products ended up right here. Okay, so if that's 0, and let's say that this right here is 100, that means this is like, I don't know, 20. So I started with 100 units of energy, and I ended later on with only 20. It's kind of like if I start the day with $100 and I end with only $20, then that means I gave up 80 units of energy, or I gave up $80. So I gave off By the time I go from the beginning to the end, I gave off 80 calories worth of energy. So energy exited. And all energy is eventually given off as heat. It might make the wheels spin for a while or whatever, but eventually all energy is given off as heat. So exo means exit, kind of like exocytosis, and thermic relates to temperature. I use a thermometer to measure temperature. I use a thermos to maintain like the hot drink that I have in my thermos. So this is an exothermic reaction because thermic, heat, exits, exo. I know it exited because I started with 100, there's this bump, and I end with 20. Oops. Endothermic goes the opposite way. My reactants are here, my products are here. So just picture a regular old chemical reaction, something like this. I might have A plus B yields C. Those are my reactants, so those would be my reactants right there at the beginning. My product would be C. Okay, so now we get to this bump. That bump is called activation energy. Same thing over here. That bump is activation energy. Activation energy. Sometimes chemists call it energy of activation, and they abbreviate it like that. So if you're thinking, my chemistry teacher did this, that's the same thing. Okay, so activation energy is how much energy it takes to activate the reaction. So maybe that bump right there represents 25. If this is 100 and that's 20, maybe this is like a 25. So that gets me up to like 125 right there. So what that means is in order for A plus B to turn into C, I have to input 25 units of energy and then the reaction happens. So we always give examples of like rolling a ball up a hill or whatever. If I roll a ball up a hill and I get it from 100 to 105 and then let go, it's just going to roll right back down. That means A plus B, never turned into C. But if I can input 25 units of energy, then the reaction goes. So the example that I give is if I have like a fire, like if I light a flame, like let's say this is a lighter. So, and I run paper through it like this. If I go fast enough, it doesn't catch on fire. Why is that? Well, because you went fast. Yeah. But as far as this graph, why is that? So take a second, think about it. Why is it, using that graph, does this not catch on fire? Or why do I not torch my finger when I do this? Bunsen burners supposedly, you know how there's like multiple like flame cones in a Bunsen burner? Supposedly the hottest cone is in excess of 1,000 degrees. But if I go this fast, I don't burn my finger. So the reason for it is, now that you've thought about it, is I have to input 25 calories worth of energy in this example. So when I run my paper through here, maybe it only absorbs 3 calories of energy. So it makes it from 100 to 103. Did it make it all the way up the hill to become charged stuff? No. So let's say I slow down. Maybe now it absorbs 10, or maybe now it absorbs 20. If I just hold it in there and it starts absorbing energy, it's like 105, 110, 115, 120, 123, 124, 125. The second it hits 125, that's when it catches on fire, and that's when it starts turning into a new chemical product, charged stuff. So activation energy, when I meet activation energy, that's the instant that the reaction happens, and then the reaction should go to completion. Now, I do understand that if I hold the paper this way, it might be burning upwards, and so it doesn't burn the bottom. But the reaction could go to completion. We'll say that the reaction will go to completion. If it was like chemicals in a jar, they would go to completion. So if I had an enzyme, the way that an enzyme works is it speeds up chemical reactions. And it speeds it up by having the right chemical and physical fit. We've kind of mentioned that before. If not, I mention it some more later on in the correct video, the one that doesn't have screw-ups. But what it does is it lowers activation energy. So because my substrate, like this substrate right here, let me make sure I'm on video. Yeah, this substrate right here has a bunch of negatives on the left and a bunch of positives on the right. My enzyme has the right physical fit. It fits it physically like a puzzle piece. I know because I literally tore that piece of paper out of this one, so I know it fits like a puzzle piece. But it also has the right chemical fit. Pluses on the left, minuses on your right. So now, when my substrate sits in there, my substrate's getting pulled to the right because plus and minus. My substrate's getting pulled to the left because plus and minus. And so now I'm stressing that substrate. So if I'm getting pulled right and pulled left, then it'd be easier to karate chop it in half. As is, it might take a certain amount of energy to like break this in half. But right there, if it's getting pulled right and pulled left, now it would take less energy for me to like karate chop it. Okay, so that means instead of inputting 25 units of energy to rip it in half, now if the bonds are like chemically stressed, if I'm stressing the chemical bonds, then now I don't have to input 25 units of energy. I only have to put in like 1 unit of energy. Well, that's an easier hill to roll the ball up. So now it's more like a speed bump. So now when I make it to from 100 to 101, now the reaction goes. So this enzyme, if I drop it from 125 down to 101, that means my activation energy is 25 times less. That means that my reaction will happen 25 times faster. If I can drop it by 1,000 times, sorry, they're cleaning the floors out there in the hallway. If I lower it by 1,000 times, it goes 1,000 times faster. The fastest enzyme that we've ever clocked runs about 10 million times faster than without the enzyme. Okay. The last example I would give is if I had this paper and I had the flame, so just like a second ago, I know that I did this a second ago, but when I ran the paper through, it didn't catch on fire because it had an activation energy this tall. Let's say that I dipped this paper in gasoline. Don't do that. But if I did, and then I ran it through this fast, it would probably burst into flames. Why? Because gasoline has a much lower activation energy. So this catches on fire with just a spark. All right. I think that is about all that we missed. Oh, endothermic. Endothermic is pretty obvious once you understand exothermic. Here, I started at, let's say, 20. Hang on, I think this is the one that writes dark. Crap. There, I started at 20. I end at 100. So that means if I start at 20 and I end at 100, that means I gained 80 calories. So thermic, temperature, entered. So this one sucks up heat. So this would be like a cold pack. If you twist your ankle and the coach has like that little plastic thing and he kind of crunches it around and it turns all slushy and cold. Okay, and it turns all slushy and cold, it's absorbing heat. If this thing right here, if chemical A mixed with chemical B starts sucking in heat and I touch it, now it's sucking in heat from me, and when something sucks in heat from me, that means heat's exiting my body, it feels cold. This guy over here is releasing heat. So if I mix A and B, kind of like a hand warmer, like those hot pack things that you can get in the camping section, if I mix A and B and they start releasing heat, then when I grab something and it's releasing heat into me, it feels hot. All right, I think we're good after that. So thanks for listening. See ya.